with probabilistic computing. The next session. Let me get some music running. The stream is going, is working. Yes, perfect, perfecto. And we will just get some right hyper-focus music.
Data annotation.
Data annotation is a fucking retarded ad. Okay. Cool. So we're going for it. We're going for it. We are going to do this one in entropy inference computation. I think I was done with these. I think I was almost done with these. I think today I'm gonna start with these. I'm gonna finish this one later. I think I was done with these. Let me go check. But I think I was done with these. Greco-futurism. Yeah, I think I was missing like something along the lines of a what's it called? Like the final summary. No, it's chapter 1, 2, 3, 4, 5 were completed. Chapter 6. Oh, we had the exercise, so we had the bias theorem problem. So we had these. We can come back to this later. I definitely want to do this one. Because here we did actually, oh yeah, cool, sure, I mean, it's cleaned up now. But like we did that, and then here's the bias theorem problem. If the probability of disease, probability of positive, given the disease, and probability of positive no disease, compute P disease if positive. And here we were essentially, yeah, you could decompose that into what we had been working before. But it's fun. I wanna cover more ground today actually. So what I will do is I'll go back here and I'll do the thermodynamics of computing session. I kind of feel like I want to get into this one today. And we'll do the exercise in the next session. That's all good. It's no big deal. Cool. So what are we starting with? We're starting with second law of thermodynamics. Oh, brother. Oh, this is so rusty. The second law of thermodynamics. Was this one the one about entropy? Computation. The entropy relating to the flow of information during a computation. Okay, those are deep questions. So let's. I need to dust out. I need to dust some of these things out. So I probably need to do some grok, some reading out loud with grok on these. So I need a refresher on entropy. I need a refresher on the laws of thermodynamics. So let's go this refresher on thermodynamic laws and a refresher on entropy. Let's do these. Let's just read through these a bit. First, so thermodynamics is a study of energy, heat, work, blah blah blah. The four laws, zeroth law defines temperature. System A is in the thermal equilibrium with B, and B is in thermal equilibrium with C. When A is in thermal equilibrium with C, this is why thermometers work, and temperature is well-defined property. The first law is conservation of energy. Exactly, conservation of energy. This is a known law. That's good. The second law is the direction of natural processes plus entropy, and this is basically that Heat flows spontaneously from hot to cold, never the reverse. From hot to cold, yes. No heat engine can convert 100% of heat into work. And the entropy of an isolated system never decreases. Okay, so the entropy either stays the same or increases. And entropy, I think, so entropy was then basically relating it, it's related to how much predictability, right? I believe there is. So a temperature approaches absolute zero, the entropy is a perfect crystalline substance. It's the minimum value. 0 Kelvin is the absolute zero. And essentially the entropy, which is what they're saying here. So the limit of entropy when t approaches zero is zero. So you can never reach absolute zero in a finite number of steps. So entropy is the state function that quantifies the dispersal of energy for a reversible process. For any real irreversible process, yeah, so the equality of reversible process is where higher omega equals more disorder or more ways to spread energy, higher entropy. Entropy is not just disorder. Yeah, that bothers me a lot. It's a measure of how many ways energy can be distributed among particles. Okay, the second law says the total entropy of the universe increases in every spontaneous process. Local order, so a refrigerator making ice is possible only because entropy increases elsewhere. Yeah. Yeah, exactly. Okay. Which is essentially to say, if you're spending energy, you need to spend energy to actually decrease entropy, right? Okay, I think it's good enough. Let's go back to the chat. So, what do you recall about the second law of thermodynamics and how it might apply to information processing? It's about entropy, right? So, as the second law that we saw is the law of entropy, that entropy globally increases. Now, I think related to the flow of information during a computation, it's like the ice cube thing, right? So I think when you're doing a computation, you're reducing entropy. But it wait, what did I say? Oh, I sent the wrong message. I was saying that with computation, you're reducing entropy. How might that principle extend to the order we create or destroy when processing bits of information? I mean, erasing information is interesting because you're not truly ever erasing information in a computational process, right? It's more of a convention to just say that information is something that I don't care anymore and I can actually override it, right? So it's more of a flag, and actually erasing information in a computational process, in a way, it's bringing some more order and decreasing entropy, because what you're saying is, oh wait, no, actually you're increasing entropy according to that concept that you can maybe distribute energy differently, right? Because all of a sudden now you have a chunk of memory that is freed and can be used, right? It's not ordered. You're just saying that's free to use, right? I think that's what I would say. They're saying we can play with them, right? They're not in order anymore. It's crazy how these things actually work. That they feed the framework, because this still feels very theoretical. Yes. Okay, chapter 2. Write down your estimate of the minimum energy needed to erase 1 bit of information at room temperature. What? Okay, that was a jump. Where do we start? Okay, so the estimate of the minimum energy needed to erase 1 bit of information at room temperature. Where do I even start? The energy needed to erase 1 bit of information. At room temperature. Fuck commercial. Well, that minimum energy would be related to the energy that the hardware needs, right? I mean, I think that's a starting point. I would say that it's related. The minimum energy needed to erase 1 bit of information at room temperature is related, proportional to the energy that it takes to run a very simple circuit board. What leads you to tie the fundamental lower bound to practical circuit operation rather than a physical limit set by temperature alone? Well, because okay, maybe I'm like too much thinking about like computation right now, as in like computers, because I was just thinking, okay, that like, well, we're talking about digital information, so that was an assumption here, definitely. I guess to raise a bit of information, it can be thought more of in general terms, right? As in like to make a change, right? To make a change on a physical system at room temperature. Maybe I was just stepping too much ahead. What quantity in thermodynamics must increase when two distinct states are forced into one? Well, that would be entropy, right? No. I can't mark it down because we need to estimate the minimum energy needed to erase 1 bit of information at room temperature. Okay, yeah, but then it's then related to the temperature of the room, right? Because that actually defines how difficult it is or easy it is to actually do stuff at a physical level. But then how do you relate temperature in a room with energy or an energy threshold that is needed to make a change or to increase entropy? These I'm not sure. How does thermal energy per degree of freedom connect temperature to How does thermal energy per degree of freedom connect temperature to the energy cost of an entropy change? Okay, that is too... I'm gonna ask Rock. I need more. I need to build some more context for these. Thermal energy and entropy. So there's a few things I don't understand. The degree of freedom, the entropy. Yeah. These guys are taking so much time. Let's think through these. So, and I guess based on what I was reading there, it's like the ln, the logarithm. Like, I think this is just the reference to the fact that we're looking at a binary system or like at a bit of information. But we're trying to connect temperature to the energy cost. Okay. Temperature to the energy cost to do that. Temperature. I mean, temperature in a room is directly something that kind of correlates with entropy, right? So thermal energy per degree of freedom. I need to open this up. That's not something I know about. So this directly sets the microscopic energy scale associated with temperature T. It connects to the minimum energy cost of an entropy change. Via this relation, an increment of U equals T times an increment of S, which is exactly the Landau limit. Temperature also links entropy and energy thermodynamically. An entropy change of these, whatever that notation means, is 1 bit. So in this context, what are degrees of freedom? Is any coordinate rotational motion, vibrational mode of harmonic oscillator. When we talk about the energy cost of an entropy change, okay, that's the interesting part. So when we talk about the energy cost of an entropy change, the bit is physically encoded in one of these information-bearing degrees of freedom. Position of a particle in a double well potential, voltage charge in a capacitor, yeah, okay. The thermal energy scale of that physical DOF sets the size of the fluctuations that must be overcome to reliably control or reset the bit. All right, so the degrees, I guess what we're saying here is we're expressing the room in as an energy function of sorts, right? And this energy function has degrees of freedoms, and these are the things that we can change in the environment. So imagine the room I am right now, it's a very complex energy function, and it has different degrees of freedom based on what I can change in the room, right? And so when we're talking about the energy cost of an entropy change, is essentially how much energy we have to put into the system to make, but it's still not clear. Let's go through these. So let's define these again. So we're talking about an energy function that kind of describes the environment, and this one has degrees of freedoms, and those are the things that we can change. And what I'm trying to relate is this concept of energy that is needed to actually make a change in one of these degrees of freedom. But this threshold, this concept, I don't really see what relationship am I using here to define that threshold that needs to be overcome. I'm assuming it's connected to temperature, but that temperature kind of does not, well, it does then show in the energy equation, does it? You're circling the energy scale set by temperature for each degree of freedom. What simple expression gives the typical thermal energy available? What simple expression gives the typical thermal energy available to a system at temperature T? Okay, yeah, that's what I'm looking for. I'm looking for these. I don't know actually. That's what I need. That's what I actually need to investigate. That's what we need to investigate. This is the standard, simplest expression for the typical thermal energy available to a system at temperature T. Okay, where Kb is the Boltzmann's constant. What? In the equipartition theorem, each quadratic degree of freedom contributes an average energy. However, the overall energy scale set by temperature why these? So it's as simple as this constant times T. It's the fundamental proportionality factor that converts temperature into an energy scale in joules. Temperature is a microscopic quantity. Energy, kinetic potential heat, is measured in joules. So without a conversion factor, you cannot equate average energy per degree of freedom directly. Okay, but but is then, like, how is then this constant set? Is this constant something that is set empirically? Because then that explains. And I'll probably have to wrap it up here, because it's a bit late and I don't have much time. I'll promise I'll try to dedicate more time to it tomorrow. We're getting somewhere though. That's definitely a much denser session. Planck's constant, Boltzmann's constant. The Kelvin is no longer defined by the triple point of water. Instead, temperature is now defined in terms of energy via the exact Kb. So, in practice, the Kelvin is realized by fixing Kb and using the cesium -133 hyperfine transition frequency together with H, but the key point is no longer uncertain. This is by exact definition. Empirically. (1.38 times to the times 10 to the minus 23 joules per Kelvin. Okay. All right. So essentially, so there's this constant that defines how many joules takes to move a Kelvin, right? Okay. What a simple expression gives a typical energy available in the system. The simplest expression is basically that the energy is the temperature times the Boltzmann constant. The simplest expression is basically that the energy is the temperature times KB. While entropy reduction relates to temperature increase or temperature decrease. When heat is released into the surroundings to raise the beat, what must happen to the environment's entropy? Then it goes up. I have to wrap it up here. Estimated the minimum energy needed to erase. Oh, is the minimum energy needed to erase one bit of information the KB constant? Is that what we were after? You're close to KB, but it's not. But that's only part of the scale. What else multiplies with KB, and what factor accounts for the entropy change per bit? Okay, so we're there almost. Like I think that's that other part. That's these ln2, right? Of K. How does thermal energy per degree of freedom connect temperature to energy cost of an entropy change? Estimated the minimum energy needed to erase that bit of information. Okay, I'll stop here. We'll continue here. Chapter 2. Chapter 3 is like, why do irreversible operations like bit erasure lead to heat dissipation according to Landauer? Let's summarize. Some reversible logic gates could avoid erasure. Schedulable reversible computing circuit, and note its thermodynamic advantages. Oh, that's interesting. Okay. Essentially, building reversible computing circuits makes them more energy efficient. Interesting. Maybe that's the key of the whole extropic thing then. Anyway, we'll get there, guys. See you tomorrow.